Hello everyone. So in this problem, we are actually studying a wire loop and it's lying in a magnetic field B, but we have different scenarios for this magnetic field. So in the first situation, we have a magnetic field that's equal to 4 times 10 power minus 2 Tesla times Y, Tesla uh, per meter times Y. So and it's directed along the positive k direction, so it's actually directed out of the page. So in this situation, we want to find the induced EMF and its direction. If we want to look for the magnitude of the induced EMF, let's remember the formula for the induced EMF, which is minus delta phi by delta t. And like we said, whenever we're talking about the magnitude of an induced EMF, we can just take away the minus sign. And the flux here is B times A. We can see that B is outside the page and it depends on Y. So it only depends on Y, and actually this means that it is not changing with time. Okay, so this one, the flux itself, will be also independent of time. Okay, we notice here that phi is independent of time. So the EMF, which is induced, which is equal to the change of the flux with respect to time, will actually be zero since phi is not changing with time here. So the induced EMF can be immediately given to be zero. We cannot have an induced electromotive force unless we have something changing in the flux. So if the flux isn't changing with time, this means that there's no induced current in this loop. And of course, for the direction, we will have no direction since we don't have any electromotive force. In part C, we are given a new expression for the magnetic field. So B is 6 times 10 power minus 2 T, and it's also directed out of the page. Now, note here that we now have a dependence on time, so we can actually expect to have an induced electromotive force. So before we do that, let's write our expression for the flux. This is going to be B times A. Um, and okay, if we want to write this down, this is 6 times 10 power minus 2t times the area of our loop. And to find the induced EMF, we will just write a derivative with respect to time and not this expression because we see that we have a dependence on time. So this will be minus d phi by dt. Like we said, we want the magnitude, so I'm going to remove the minus sign. We're actually looking for the magnitude of the electromotive force. And now we want to just derive the expression of phi. And this will be 6 times 10 power minus 2. The area is independent of time, so I can take it outside the derivative. And this is just dt by dt. So this is actually the derivative expression for the induced electromotive force. If we substitute the value of the area, so we are given the length is 40 centimeters, which is 0.4 meters. The width is 25 centimeters, so this is 0.25. And this will give us actually 0.006 volts. So this is the magnitude of the induced electromotive force. We were asked also for the direction of this induced electromotive force, and like we said, we just look for the change in the magnetic field. The magnetic field here is increasing, so phi is increasing, so I induced will be such that B induced is opposite to B. So B here is along positive K, which is out of the page. So B induced will be into the page. And if we apply the right-hand rule, this means that I induced is clockwise, and so is the induced electromotive force. So B induced is going to be along is going to be into the page. And so by the right hand rule, I induced is clockwise, and so is E induced. We still have more expressions to study. So in part E, we are given this magnetic field, which is equal to 8 times 10 power minus 2 yt, and it's also out of the page. So here we actually have a dependence on y and a dependence on time. So if we have a dependence on a position, um, then this is not a uniform magnetic field, and to find the flux we're going to have to integrate. Obviously we have a dependence on time, so this tells us that phi will be changing, and so we can expect an induced electromotive force. So let's write down our expression of the magnetic field and try to see if we can actually get an expression for the flux. So B is 8 times 10 power minus 2 yt, and this is again along positive k, so it's out of the page. We can find, let's start by finding the flux, an expression for the flux. So since B depends on position, then the flux will have an expression of B, an integral of B dot dA, and we actually need to take some infinitesimal area to integrate over. Now we see that B depends on the Y position and not the X position. So it will make sense that for our loop, we can consider um, maybe a horizontal strip. So we take this horizontal strip of width dy and length L, and then we integrate over y. So consider a horizontal strip of area dA, which is equal to the length times dy. So we can now solve for phi. It will be the integral of 8 times 10 power minus 2 yt. This is the expression of the magnetic field. And dA is L dy. So we can now integrate. I will just leave y dy inside the integral, and the rest can actually be moved to the outside because they are all independent of the y position. And this will actually give us y squared over 2 with y varying between 0 and the width of our loop. And now all we have to do is just substitute. So we know the values of the width, the length, and so on. So this is going to be 8 times 10 power minus 2 times TL times W squared minus 0 over 2. We will leave phi in terms of T, of course. And then when we find the induced electromotive force, we can substitute the value of T if we still have any time in the expression. So if we actually solve this, we will get an expression for phi, which is 0.001 times T. And if we look for the induced electromotive force, this is d phi by dt, which will be 0.001. So this is our expression for the electromotive force. Let's look for the direction again. Our magnetic field depends on y and t. Everything here is positive. Y increases, t increases. This means that the magnetic field is increasing. So according to Lenz's law, the induced current will try to oppose this increase in flux. So if B is outside the page, the induced magnetic field will be inside the page, and by the right hand rule, the current is going to be clockwise. So the induced EMF will also be clockwise. We still have more expressions to study. So in part G, we have 3 times 10 power minus 2 xt, and we want the induced electromotive force again. Now, the direction of the magnetic field here is along J. So it's along the positive y-axis. This is the direction of the magnetic field in part G. So if the magnetic field is directed along positive y, then actually there are no field lines entering in this loop. And then there is no magnetic flux because the angle between the magnetic field and the normal to the area is going to be 90 and cosine 90 is 0. So in part G, the flux is actually 0. So since B is along J, then phi, which is BA cosine theta, will be 0 because theta is equal to 90. So the flux is going to be 0, and then the induced EMF is just going to be 0. There is no flux passing through our loop. And for part H, there is no direction to talk about. Lastly, we have this last expression. B is 5 times 10 power minus 2 yt along positive I. So this is a changing magnetic field with time. The flux is changing, but again, the direction is along positive x. So it's in this direction. And again, no field lines are going to pass through my coil. So there will be no induced electromotive force in this coil again. So in part I, B is along the positive x-axis, which is the direction of I. So phi is equal to 0 since theta equals 90. This is the angle between the magnetic field and the normal to the area of our loop. And of course, there is no direction because there is no induced electromotive force. So here we had different equations and different expressions for the magnetic field, and we were checking what will happen for these different expressions.